Page 3 on physics and such. Yeah, I started this video the other day. It didn't work out. Anyway, so I'll respond to two comments basically made in the previous video. First on Feynman's attitude, and I don't want to get into a whole argument about it. So a clip was provided of him, and I didn't think it said much, and I think 5 minutes later he said something, likewise still arguing that the model, there's points where you can find he actually recognizes the fact that we need a model. We don't have a model, but he doesn't say it overtly, and I think it's important. And I just think that physics is sort of important to have the model, not just the math. And the math is this is the part that gets tricky, is that quantum mechanics is a diagram that a way of looking at what's happening in the reality that mathematically works because it is recognizing the broad form of the reality and duplicating much of it, but there are a lot of fixes they have to apply. They have to change a constant from a +1 to a -1, or they have to add a number, or they have to have some other compensator for the fact that there is some missing bits. And I just think that's important to recognize, and that I don't have a good metaphor for it, but I think for the fact that there's a gross similarity between what reality is doing and what you can conform it to based on the principles of reality. It's almost like the lens, it forces a kind of shape. Now, the part that reality is working with is this part of the shape, say the middle part, the focus. And the rest of the part is just a physical reality, that in the real world you can't do anything but slope a surface end to end, or that there's natural curves created by like a water bubble. There's a natural tension that creates a natural curve, and that those circumstances have a parallel to the internal circumstances. Like the mechanics in the big world are not completely without correlates in the little world. And so our big world math will apply to some of this little world circumstance. And yeah, something like that. So anyway, but I don't want to get into an argument about, I just think it's important for physicists to work on models, that's all. He just doesn't seem to think. I think there's just, for a lot of reasons. The second argument I would make is that he spent his 4th video in that series just wasting time, in my opinion, talking about obscure particles created in accelerators that have lifespans of milliseconds, and you're just saying why. Those parts are not even, I don't know if it's even worth giving them names, because they're parts of structure. So there might not be real things anyway. They're just what you're likely to create when you crash two cars together. Yeah, you're likely to cause certain big pieces to fly off, engine part or body part or bumper or wheel, and yeah, it has a vague similarity to those pieces, but they're not really similar, so I just don't see much use in that. And we know what most of the matter is doing, and we know what most of the matter is involved with, and so that's probably the place to start in terms of understanding. I don't know whether this other stuff has too much to do with what really is happening. Yeah, I don't want to go too far, so yeah, I'll just leave it at that. I just think it's really important to try to say what we can say in terms of a model, and go as far as people can. Try these different approaches and then see where they fail, and try and somebody should be kind of indexing those failures. Well, anyway, And then the other thing that Hofstadter brought up was the Bell's theorem, inequity theorem, whatever the hell it is. You know, this disputing of the fact that there's some sort of hidden variable or written character in any matter that is somehow associated at a previous point, that it gains a certain state change, a certain condition that it shares with stuff it's interacted with, would be the argument. And that might be all the way fundamental as Big Bang. The Big Bang might be inside of all of matter, might have a vibration relative to that event. And the problem with all the proofs of Bell's theorem, the proofs I've seen, is that they all rely on some sort of staged process experiment that requires the detection of photons. And now we're back to the two-slit problem, where you can't really detect a photon realistically. You can't. You know, certainly not without having some effect of erasure, not without completely annihilating either its polarity or some other aspect of it. So there's just no point in doing an experiment and saying, look, the results are different than QM, and it's because of blah blah blah. And no, it's because you are claiming you can do something you can't do, which is passively detect a photon. So that's where I would leave that. I'd say, you know, there needs to be a lot more work on Bell. Alright, questions I left on the last video were this idea of how big stuff is, how much of it there is, and it's this, you know, the very idea that an atom is to an apple what an apple is to the earth, and just thinking in terms of those, you know, in terms of that number and how small these things actually are. Would be interesting to know what the relationship between a photon and an atom is. So, you know, if the Earth is to an apple, what an apple is to an atom, what is a photon to an atom? And I wonder if the relationship is extreme. Alright, so the other thing I'm going to, there's two, I guess this video I'm going to try to stick with some idea of understanding the spectrum of photons. And photons really are it's photons and electrons, and we could argue that the interior of an atom is probably made up of some combination of electrons, or things like electrons, whatever. But I always come back to some sort of, I think it gets simpler as you get deeper, and that there is some fundamental particle, a quanta, that it establishes, you know, it's working and it's functioning in some sort of three-dimensional grid, that it has a very simple capacities. You know, it might have this simple idea of a north and a south side, and you know, a polarity, and you know, it just moves the speed of light, and at essentially a clock speed. So it might be argued that it can move the speed of light in any direction. You know, that doesn't matter, and as long as it does it within that clock speed of the Planck constant, which would be the distance, you know, that the quanta would be. So essentially it is a domino kind of thing. The domino has a specific size. When the domino flips, it moves a specific distance, and that would be a Planck constant. And so there's something like that at the root of the whole thing. What I'm thinking about too is so there's two things I want to get to here, is the structure of what shapes these things could take that would be conducive to their binding. And so let's do the binding part first. So it's my contention that atoms, so if this was a nucleus of an atom, what I'm sort of thinking that might be possible is that the orbitals are really quanta in arrangements, electrons, and that electrons might be like a double helix electrons might be a spiral of two photons. They can be connected or not connected with bars between them, let's say, and that they rotate. And it's through that rotation on this axis, spinning, that their speed is changed, because now they have two directions. They have a forward, let's say, direction, and they have a internal spin direction for each strand. So you could argue that depending on how tight this weave is, this wave spin, would dictate how much room there is for speed. So if they had a very long spin, they could move very fast in this direction because they're not using up their speed of lightness, and so they could come closer to the speed of light in this forward direction if their spin is very slow. If their spin is very high, then they can only move some fraction of the speed of light. But let's say they could be in an arrangement of this head to tail kind of idea, so that quanta, or photons, could be in a relationship where they are bound together, head to tail, in a head to tail spiral, and that would be a form they could be in. And then if there was even another form for even photons or other binding bits that could be in that same kind of relationship, except maybe it's overshot or undershot. But let's just say overshot for the sake of this argument. So instead of being symmetrical, they could even have a deeper spiral. The point would be is these could end up being a kind of locking device. So, and these two could be. So it just depends on how how far you take this. But obviously you could see that if we said this was spinning in the arrow direction, it could loop into one of these locked, say, electrons, and it could become a link. And so anything that came in contact, if another link came in here, it would, just by its nature, just because it has this open end, it would become a locking device, and it would end up locking two of these spirals together. So I have a vision maybe of a remodeling of the atom as these locking spirals of electron. And so then you would have the same idea, you'd end up with something that had the same size as what an atom is stated to be, theoretically, through these loops, and the fact that you would have outer rings that would have more electrons and inner rings that would have fewer, and it would just be based on how many rings could be contained within some internal locking device. So they're locked from the nucleus, and so your typical hydrogen would just have the one, then helium would have the two, say, opposite each other, and lithium would go with the third. It'd have to be in the next, maybe locking these two together. But it could just be that it starts to do this Mickey Mouse ear thing. So essentially it's just a bunch of these Mickey Mouse things, where 3 would be the locking number, and you can end up with the appropriate numbers depending on whether you establish as 2-based or 3-based. So I don't know exactly what specific observations dictate the nature of the orbits, but the point could be is that the ones that have not captured an electron may well have this lock. So they have a lock, just looping open and on an electron, and that's why it's conducive to binding to another atom, is because it has these available locks that have not captured anything. And so that would explain why when two atoms contact each other and one of these orbits is empty, that this locking loop will lock into that electron on that atom. which makes sense to me. The idea of a lock makes sense. So I like this locking idea, that you have these locking devices that might be made out of bosons or whatever, some of these eccentric particles. You know, the created particles, you could argue, that might explain that. So anyway, this obviously needs development, but I'm just saying there's a certain number of arrangements you can come up with for what this quanta would do, and it can't get too complicated. So I think you can have these closed loop spirals, and you can have these helix type arrangement, and maybe there are some other arrangements. So if you have some ideas on that, that might be interesting. How you could connect, say, little, I have to get out my magnets, you know, magnets together into stable relationships. And I suppose the most important one would be, you know, finding a physical description of what might be one of these locking devices. That might be something like a photon, but obviously I have to explain why a photon would be looking like that. How exactly in principle it would have that nature. Like I said, the electrons themselves could have that nature just from the fact that the head-tail thing doesn't work entirely, that they're attracted, but the attraction isn't complete enough. It isn't closed, and it leaves the opportunity for this gap where the rings can lock. Magicians used to use rings that had little breaks in them, you know, and they'd push the rings together and fool people because the rings had little breaks in them. You know. Anyway, same idea of locking rings, but I like the idea of locking rings as a model, as an explanation. Alright, the thing I want to get to too is frequency and amplitude. So, you know, this whole electromagnetic scale thing where you got these cosmic rays, let's say at this end, you know, you got X-rays, you got microwaves, and then you got light, and then you got whatever, radio waves. It's probably something else down here. So you have this scale of what photons, the varieties of that photons come in. And we sort of been fooled by, you know, parts of this spectrum, you know, this tiny little bit of visible light, this tiny little band, and we have lots of descriptions in here. We got red, and then we got green, and then we got ultraviolet, and then we got infrared, and so we're very specific in naming this little tiny bit, and the rest of it we're just like, oh yeah, they're all one of those things. And so we have no more detailed description. And part of that is relevant to the fact that most of the light created by a sun, or you know, most of the energy binding that's going on in the universe, or most of the interactions that are taking place in somewhere in this range. This is the substance of the active parts, the parts that are active inside of atoms. There aren't too many radio waves inside an atom, and certainly all this other you know, high energy little stuff isn't too active either inside of an atom. Atoms aren't, generally speaking, radioactive. It's just a few of the most eccentric atoms that are. So anyway, what I'm thinking, so you have two aspects to what's going on here that we know of. And you have, like, energy, people talk about that, and you have frequency. So I guess you could argue that the energy would be what people might generally call amplitude, but it might just be another way of saying the number. So the number of photons is going to affect how much energy you're going to get, and then you got the kind of photon would be the frequency. So that one's another one we already have established. This is a frequency gradient, that the color differences in light is a function of frequency. So they're at a different frequency. Red's different than blue in frequency, you know, which might be size. So that's how I'm going to break it down. There's two things. There's a kind of photon in terms of its size, and then there's the number of photons. And so with radio waves, what it is a very long photon, you know, meters long maybe, and it's its frequency, just because of the fact that it's very long. You can't have too many of them. You know, you can't have too many too often because it's very long as a photon. So it can't. You know, it can also, you can create a band of radio that has inside of it many frequencies. It could have a long one, a short one, a long one, a short one, and we have this illusion just because it is all happening, you know, without our being able to see it, that's what's happening, is that it's multiple layers of photons at different frequencies. So there's, you know, more than one photon being created, and they're at different frequencies, and we consider that somehow one thing because we don't detect it with a lens, or we don't detect what's coming in, and we don't make differentiations. So we see it as being one thing, a radio wave, and a radio wave isn't one thing. It's a whole band, it's a whole spectrum of different frequency, different length photons coming towards some general source. So the amplitude is a function not only of the strength of the strength of a signal is more than just the function of how many there are in length. Obviously the length can make something look like a lot, but you can also have a lot in terms of they're not following each other, they're independently produced at different time intervals, so it's creating more than one stream. So we think of light as being a stream of photons, like a laser beam almost. We think of it as, you know, it bounces, it comes into us, and it's a stream of fed in photons. It's not just one photon, it's a stream of photons that make things visible, that we stop seeing as soon as the stream stops coming. So the stream keeps feeding the signal, and we think of the stream as being behind each other, one following the next of discrete photons. But the signal can also come in, you know, clumps of not clumps is probably the wrong way to say it, but as a mass that can be much bigger, that has lots of different lengths of, or, you know, lengths. It's all, you know, that's what my argument's going to be, is that it's made up of, that frequency is a function of the length of a stream of quanta. So you have quanta, you could have like we could just make up a number of quantas that are, let's just say 4 represents 1,000,000, and so you could have 500,000, and then you could have, you know, 1,000,000. And what's happening at the high end is that they're smaller, but they're always produced in much larger numbers, and that would account for their aggressiveness in terms of they're probably produced maybe of short duration, like there's a bunch of them going horizontally, and we have no way of detecting the mass of them moving in one direction this way, or a mass moving in this direction. And obviously, I think obviously, one could argue that they're going to have different effects depending on whether their mass, their substance, is bang, 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 like 15 machine gun bullets, or one shot all at once, really short duration, but it's really a thick shot. So it's the difference between a lot of little bullets in a row, or one big bullet. Something like that anyway. But yeah, these would be the smaller bits. So the bits that are able to, makes more sense that they're able to get through things, that they're not absorbed or blocked. They can be absorbed, but that they're not blocked anyway as easily as the bigger things, the that size would make a difference in terms of the capacity of the thing to get absorbed by something, because it's connected to all these other parts. So you could argue that if a stream is coming into an atom or interacting with an atom, and it's a long stream, bound stream, that there's not much, it's not as easily for something to consume it. It could, bend it easier, but it's not going to consume it as easily because it has some, the fact that it doesn't leave an opening, a tail, that, that might have some impact on the fact that if you can't break it, you can't grab it either. You could, because I can't say there'd be momentum, because momentum wouldn't make much sense on that scale. But just the fact that there are physical properties relevant to photons in this very long condition versus photons in this very short condition, and there would be advantages and disadvantages depending on what matter you're interacting with. Size will matter based on what you're interacting with, and that would have more to do with whether something's going to be absorbed and whether it's going to be reactive to the substance it's interacting with. Something like that. So yeah, maybe that's, I won't push it too far. I like the idea of a clock speed, of course. It would be just a metaphor, because you could argue you don't need a clock speed if you just have this established idea of a piece of matter that moves, a constant distance of space, and that just automatically creates time. If you create distance, you create time. If you create time, you create distance. There's just no way of getting around that interrelationship, and that there's bits that make up the parts that are going the speed of light. So part of this thing would theorize that all energy is quanta moving the speed of light. So all energy is made out of this, and all matter is just arrangements, binding arrangements of things moving the speed of light. So they've just been trapped. So the stuff moving the speed of light is trapped in relationships that consume its speed of light in some benign way. So the speed of light is still there. There's still quantum moving the speed of light, but it's trapped in some sort of circumstance that no longer creates linear distance. The distance is circular and spiral in nature, and it consumes what one would think would be its impact. So you could look at the moon and say it's a bullet flying through space, but now it's a bullet trapped around the Earth. So it's been made inert to appearance, to function, in the sense that it doesn't seem very threatening. But the fact is, it's just as threatening. It's still a bullet. It's still, it still has all of its properties, and it's just trapped. And the minute it's not trapped anymore, it's going to be a hurling meteor, a big giant meteor flying through space. So, so that's all an atom is the confinement of quanta moving at the speed of light, and that everything's made out of stuff moving the speed of light. And this gets to the paradox where I argue that the reason why matter can't travel very fast, relative to the speed of light, it can move fast, but not relative to the speed of light, is that the internal quanta are already moving the speed of light. And they're already moving the speed of light in orbits. And if you're going to change their speed, you're going to have to reorient them, not actually move them. If you had to actually push them, you might end up, like I said, if something's caught in an orbit going like this, in this direction, and I try to make it go this direction, and it's already moving the speed of light, the paradox of the problem is obviously I would be, at this point, let's say, it would break relativity. it would have to move faster than the speed of light here to end up in a spiral here. So that's not going to work. And the way it could possibly work is that this has to be broken, this circle, and that the quanta has to take another step forward on the Planck, on the clock speed. So if these were a billion, if there were a billion quanta in here, and so you have a billion clock ticks, one per billion, you could afford to take one step forward in this direction. So that's the fastest you could go, would be 1/billionth of the speed of one. Yeah, it would be a scale where you could only do it at a billionth of whatever the native frame rate of the universe is. You'd have to go a billion of those frames before you could take another step in this direction. But the point would be is that you'd have to orient all this matter so it would be moving in the right direction. Because if it's moving at the speed of light in the wrong direction, if it's going in the opposite direction to the movement you're trying to create or produce, then you're going to have to spin it. Well, it's obviously moving in both directions, in the sense that if it was aligned that way anyway, but it really depends on its alignment, right? I mean, that's another thing that has to be thought of here. You have to think of a sphere, and you have to think of it spinning in any particular direction, but that these spins would have to have an arrangement inside the matter to hold it together. So what's really has to happen is as there is an obligation to move, that obligation has to be realized by reorienting the internal matter to be able to have a net effect of movement in a direction. But the net can only be achieved quanta at a time. These quanta still have to do their thing from their perspective, which is just moving that Planck constant. And so I haven't been able to, it's really hard to work it out as a functional model inside our head, just because we're talking about something, how do you do frame rates this fast, and then try to understand, that you're moving something, to do one tiny thing, like my finger moving, there'd be zillions of operations in that, in terms of the matter moving and rotating and changing to accommodate that movement. And so obviously that's really hard to put into your head, but it's hard to put into your head that finger has the moon to an apple amount of atoms in it. It's yeesh, hard on the brain. So anyway, I think that's enough for this video anyway. So I'll get back to some of this quantum stuff and the relationship math, because some of that is interesting, especially with lenses, and because some of this quantum stuff is just relying on the fact that it takes light longer to get through a lens, because it's interacting with the matter, and keeps readmitting the light, let's say, as it travels through here. So it gets slowed down in essence, but it's not really getting slowed down because it's interacting. And so quantum is just relying on the fact that lenses do have this shape. And so it's saying, let's do all the permutations possible for what a photon could do, and then we'll be able to figure out what the outcomes will be based on these changes in time that'll be created by assuming a correlation between how fast it gets through this thing, based on its thickness. So it's a relationship of probability, but I don't think in the real world any of the photons are doing this. Okay, I don't think that's happening. I mean, certainly not one photon wouldn't do something like that.
So there's absolutely no probability that that's actually happening, and what's actually happening is something in this realm. And but anyway, I won't get into that whole thing at this point, because I have to think it through some more. But anyway, it's just a model for, I'm just saying the shape is what is what quantum mechanics is, just dealing with these shapes, and it's dealing with just defining all the possibilities the shape provides, and then doing math on that, and just coming up with a simple observation that, yeah, this is where the probability is the highest, which isn't saying much. I mean, you could almost say that's obvious from just looking at it. But anyway, I won't say that. Anyway, I'll get back to that. So anyway, yeah, no, it looks like a big enough mess. But I like this lock thing. This is you know, it's always something that catches me, and I just say, oh, that makes sense. A lock. And there's a simple diagram of a lock. And so I have those things every now and then, and they just stay in my head for a month, and then a month later I'll say, I don't know. You know, we'll see. I don't think that one's going away for a while. That one looks pretty good. Anyway, till next time.